Today we are performing another example with Nastran Solution 200. My name is Christian Aparicio and I'll be walking you through today's tutorial. Now this is our goal. We are going to take this very simple truss that you see here on the left. We're going to let the cross-sectional areas vary. Our goal is to minimize the weight from 4.82 to a new value of 2.7. So now how are we going to get through, or rather, how are we going to obtain this new optimized model? I'm going to briefly discuss how this structural model is configured. I'm going to then specify what the optimization problem statement is. Then I'm going to walk you through each step you need to take in order to convert your BDF file to Solution 200. I'm going to talk about how to specify your design variables, your objective and constraints, how to perform the optimization. Then after that, we're going to look at the results. And at the very end, we're going to look at how to convert our original design, how to convert it, or rather how to update it with the new optimized structural parameters. So like I said earlier, my name is Christian. I'm here to support you with any Nastran Solution 200 questions. You can contact me at this email address. If you're a professional engineer and if you have training questions, if you have general optimization questions, you're welcome to contact me. Now, if you're a student or a professional engineer, you can get access to the Nastran Solution 200 web app by emailing me. Now, this example is found in the MSC Nastran Design Sensitivity and Optimization User's Guide. This is available in Chapter 8. This example is known as the 3-bar truss example. This is a very introductory example. I think many new users will encounter this example, so this is a very good one to demonstrate for Nastran Solution 200. Now, let me talk about how the structural model is configured. Here, each end that you see here as I highlighted with the laser pointer, it will be fixed. And I will have to double check that in a moment. We are going to say the stresses should be between negative 15,000 psi and 20,000 psi. This is going to be for subcase 1. Actually be worth showing you what this looks like in Patran. So let me go ahead and import this model. Now let me confirm the boundary conditions for a moment. In the example I just showed, it said that the boundary conditions are supposedly fixed. So I want to confirm that right now. So these 3 nodes are fixed. You can see there's a load being applied in this direction. If we switch over to the next load case, you see that the load for the second load case is applied in the almost opposite direction. Now let's go ahead and look at the results real quickly to see what our current stress state is. Let's go ahead and do that. And then I'll want to look at some tensor plots. So here, let's go ahead and look at just the axial stresses. And it might be worth increasing the size of this. Let me see how big I can get it. So here we go. That's okay. So here you can see what our current stress state is. We have about 13,000 psi here. We have about 4,000 psi and a compressive stress of 9,000 psi here. So this is for load case 1. Let's check out what the stress state is for load case 2. So here we see almost the opposite in terms of stresses. So this is what we want to take into account when we're optimizing this. We want to do the following. We want to let the cross-sectional areas vary between 0.1 and 100. We also want to make sure that the area of element 3, so that would be this element here, we want to make sure that the area is also the same as the area of element 1. So we are going to impose what's called a variable length. We want to minimize the weight. But we also want to make sure that the actual stress for elements 1, 2, and 3 are between negative 15,000 and 20,000 psi. Also, we want to make sure that the displacement at node 4 is within a range of negative 0.2 and positive 0.2. So here's just a quick snapshot. Let's go over the steps that we'll have to take. Start with the BDF file. Your pre-post processor has produced a BDF file. So here I've already constructed my truss. I've already loaded it and so on and so on. There is a BDF file that's been created. So here in the same folder as my Patron database, my data BDF file is here. If you want to follow along, this example can be found in the user's guide. So let's go ahead and open the user's guide. And let's scroll down to tutorials. And let's look for this example. 3-bar truss. We'll go ahead and download this BDF file. Let's go ahead and right click it and save the link as, and I'll save it to my desktop. So you see that my starting file is now on my desktop. I can then continue on with this tutorial. So once you have this BDF file, you then need to go through the process of configuring this file for solution 200. You have to convert the BDF file. All the variables, the objective, and constraints we just defined, we have to express this in Nastran keywords. The great thing about the web app, as you'll find out in a moment, it automatically generates the keywords for you. After we configure the optimization, we'll perform the optimization with Nastran, and then we'll look at the new optimization results. And then at the very end, we'll update our original truss with the optimized cross-sectional areas. So let's go ahead and start the tutorial. Again, the web app allows you to take an existing BDF file and convert it to Nastran Solution 200 so you can perform an optimization. So now let's go through each step you need to take for that. Let's go ahead and navigate to the web app. So here I am in the Nastran Solution 200 web app. Let's go ahead and click on the size web app. And here I'll go ahead and upload this BDF file to the web app. The web app has gone ahead and identified all the properties that can be set as design variables. I know at the beginning I want to set the 3 cross-sectional areas as design variables. And of course I want to let the areas vary between 0.01 and 100. So let's go ahead and update the bounds here, here, and here. And we'll do the same for these other design variables. Let's go ahead and talk about our design link. So here I'll click on create D-link. This is where I can say that design variable 3 should take on the value of design variable x1. Here what this is saying is that the area of element 3 will be equal to the area of element 1. That's what the D-link is representing. Let's go ahead and move on to creating our objective. Here we'll go ahead and set the weight as the objective, and we want to minimize the weight. Now for the constraints, we see that we have a long list of responses that we can set as results. What we can go ahead and do is look for the stress constraint, and we'll go ahead and select this one time. We'll go ahead and say that we want to apply this to any element associated with P-rod 11, 12, and 13. It's not visible here in my pre-post processor, but if you look inside of the BDF file, you'll see that you have 3 properties, P-rod 11, 12, and 13, with areas 1, 2, and 1. These are used to assign the areas to element 1, 2, and 3. What we have to do is apply a constraint to those properties that then get applied to the elements. So let's go ahead and say I want to constrain the axial stress, so that's item code 2, and the lower bound will be negative 15,000 and the upper will be 20,000. And so that completes the creation of our stress constraint. Let's now focus on our displacement constraint. So here I'll type in displacement, click on the plus icon. This will be for the X and Y direction. So you can select one here, but then you have to create a second constraint and specify 2. Alternatively, you can say 1, 2 here. So this is constraining the first and second components of displacement. This would be for node 4, and it's allowed to range between negative 0.2 and positive 0.2. Let's now go to the exporter and download these BDF files. The BDF files are contained in a zip file. What's special about the zip file is that in addition to the BDF file, so here the model BDF is the newly converted case control section and bulk data section. The design model has all my statements for the design variables, my objective and constraints. But what's special about the zip file, inside is a shortcut. When you open the shortcut, it opens Nastran, it performs the optimization, all the while the web app is monitoring the progression of the optimization. So here it's gone ahead and finished the optimization and then loads the results. We should always inspect this first message. If it has a green checkbox, it means the optimization has gone through successfully. Here it says run terminated due to hard convergence. Perfect. The optimization went through successfully. Here the first plot is showing me the objective. The objective went from a weight of 4.82 and it ended at a value of 2.7. Let's look at the normalized constraints. I see that we have an initial negative constraint. This negative value means that the constraints were being satisfied. Here you can see at negative value still constraints are being satisfied, and as long as the values are less than, I believe, a tolerance of 0.003, that means your constraints are being satisfied. So everything looks good. All of the values are less than 0.003. Let's look at the design variables. We see that design variable x1 and x3 are taking the same value. So here you can see at the beginning they have a value of 1. After the first design cycle, they both have a value of 0.711. And the reason they are sharing the same value is because we have the requirement that x3 is equal to x1. As for design variable x2, we see that we start at a value of 2 to minimize ultimately to a value of 0.3283. Now, one thing we want to always do is we want to look at the results in our pre-post processor just to make sure everything is okay. Now, what you can do here, let me go ahead and delete the old results. In the Nastran directory where the optimization was performed, there's a new result file. Here, in my case, it's an OP2 file. For you, it might be XDB or some other result file. What's important to know about this result file is that inside of this result file are results for the new optimized model. So here, let's look at the results. Here you can see that I have 4 sets of results. This first selected set of results are the stresses for the initial design load case 1. Remember I said that the stresses were 13 psi, 4,000 psi, and negative 9,000 psi. We now have a second set of data. You notice at the very end, it says D7. The D's are markers. D0 is for the initial design. D7 is for the final design cycle. Here, if you notice, the final design cycle is 7. So these results are the optimized results. And pay very close attention to the stresses. Here we see that the stress is now 20,000 psi, 13 psi, and negative 7,000 psi. You notice that this element is already touching the upper limit of our stress constraint. If we look back in the web app and look at the constraints, we said that the upper limit is 20,000 psi. So what the optimizer has done, it's varied the cross-sectional areas until one of the constraints was violated. Here, element 1 is now being violated. Here, I can repeat the process for the initial design cycle or the initial model, second load case. Here is the second load case, final design. And here, like before, you see that this element is now experiencing the maximum constraint of 20,000 psi. One other thing I want to show you, the design, or rather the normalized constraints plot. These constraints are not actual values of the stresses. For example, the 20,000 psi here, that is not actually reported in this table. Instead, the 20,000 psi is converted to what's called a normalized constraint value. So here, it's sort of tricky at first. You may not know which exact constraint is causing this normalized constraint value. What you can do is go to the results section of the web app and click on responses. You can upload the F06 file. This app will parse the file for you and it will extract all the responses for you. So here, let's look at the web app again. And you'll notice that R1 is the stress constraint applied to any element associated to 11, 12, and 13. So if we look back at the responses, we see that we have two responses here. And these first two responses are for the stress constraint for load case 1. And we have a second set of data for load case 2. Now, keep in mind that we've defined one row for the stress constraint. But back in the responses table, we see that we have two results, two values for that one row. What's happening here? Here, if we click on this blue icon, we see that this first row is for element 1. So here are the element column. You see that this value is corresponding to the axial stress of element 1. This second row is corresponding to the axial stress of element 3. Here, if we look at the next row, this is the axial stress for element 1, but it's for load case 2. The next row is the axial stress for element 3, both for subcase or load case 2. Now, what you can do in this table also, besides looking at specifically what elements, what nodes are causing these constraint values, you can also look at which constraints are dominating each design cycle. So here, if you pay close attention, we have negative 3.2, negative 5.8, negative 1.79. These are the same normalized constraint values that are reported here in this table. I have negative 0.32, negative 0.0058. Let me make sure that's being reported here. Exactly. So remember what I said a moment ago. This table of normalized constraint values, these are not actual values of the stresses or the displacements. They're normalized constraint values. You can use the responses table to identify which specific quantities that may be. So here for the initial design cycle, we have a normalized constraint value of negative 0.32. If I go back to the table and I click this blue icon, I know that this is the actual stress for element 1 of subcase 1. And here you can see that essentially element 1 of load case 1 is dominating each design cycle. Here you can see that for the sixth one, it's still element 1 axial stress that's dominating the optimization. So here, negative 0.001 is the value that's reported here in bold. So the reason I wanted to point that out is sometimes you might have to dig into the actual data and look at specifically what's being done by the optimizer, what quantities are being singled out by the optimizer. So we went ahead and looked at the results. We looked at the new structural results. Here's just the optimized stress state. Remember that one element is now reaching the upper limit of the stress constraint. But besides that, all the other constraints are being satisfied. The weight and from the plots you saw went from 4.82 to a new value of 2.7. And the last thing I want to do, I want to show you how to convert your original BDF file with the new optimized parameters. So let me minimize all of these windows. Remember that this PDF file has old data for the PROD entries. We have areas of 1, 2, and 1. These are outdated, so what I'm going to do is make a copy of this file. I'll call it updated. And I need to obtain the new optimized parameters. So in the Nastran directory where the optimization was performed, there is a new PCH file. Open this PCH file. You'll see that these PROD entries have the optimized cross-sectional areas of 0.83, 0.32, and 0.83. So what I can do is open the updated model. I'll move this to the right. I can delete the old PROD entries, and then I can simply copy the new ones from the left and paste them here on the right. I can close these old files, and then I'll save this new file, and there we have it. This new file on my desktop now has the updated PROD entries that have the updated cross-sectional areas. So this model is now optimized. So I believe that was the last thing I wanted to leave you off with. Just a quick reminder that if you are a professional engineer and you have questions regarding Nastran Solution 200, feel free to send me an email with your question, and I would be more than glad to get back to you with an answer. If you are a student or professional engineer, you can get access to the Nastran Solution 200 web app by also emailing me. With that, I'll stop the video, and thank you so much for watching.